True or false? The orthogonal projection of a vector y onto a subspace W is denoted y hat, or the projection of y onto W. True. Okay, true or false? Y hat is the point in W closest to y. True. And you get the last point for free today. Okay, so 6.3 is just expanding our definition of the orthogonal projection of a vector. Rather than just projecting onto a line, you can project onto a subspace of any dimension. So here's some pictures of what we're doing. And these aren't in your packet, but they're in your book, and they're in Caitlin's notes on the reading that it's in Moodle. So rather than just dropping a perpendicular from a point that you're looking at to a line, right, you can drop a perpendicular from a point to a plane and find the orthogonal projection onto that plane. So this can be done in more dimensions than we can visualize, but so this is basically what you're doing. Y hat, so when we went onto a line, we just did y dotted with u over u dot u times u. Now, when you're going to go onto a plane, you do that over and over again, once for each u in the basis, in the orthogonal basis of your plane. So in this case, I have u1 and u2 form an orthogonal basis of this plane W. And so I just do the exact formula I was doing before. You just have to do it for each vector in the orthogonal basis. Okay, so here's my example. I have y, u1 and u2, and I have a plane that is the span of u1 and u2. So it's a plane in R3 spanned by these two vectors. And in order to use my formula for finding y hat, u1 and u2 has to be an orthogonal basis. We know that it's a spanning set. It's linearly independent. You can tell by looking at them because one isn't a multiple of the other. So we know it's a basis. So we just have to show that they're orthogonal. So you just take their dot product and you get 0. So u1 and u2 are orthogonal. So u1 comma u2 is an orthogonal basis. All right, since I know that u1 and u2 form an orthogonal basis, I can find the orthogonal projection of y onto w, which we call y hat, typically denote y hat. And the formula we used before was y dotted with u over u dotted with u times u, right? But now I have to do this twice, once for each vector in the orthogonal basis. So I'm going to put 1s here, and then add that to y dotted with u2 over u2 dotted with u2 times u2. So y dotted with u1, that's going to be 2 plus 6 is 8. u1 dotted with itself, that's 1 plus 9 is 10, times the vector u1, which is 1, 3, 0, plus y dotted with u2, so that's negative 6, plus 2 plus 6 is 2, over u2 dotted with itself, which is 9 plus 1 plus 4, which is 14, times u2, which is negative 3, 1, 2. So to get some ugly fractions here, I'm just going to multiply my 8/10 times every term in here, multiply my 1/7 or 2/14 times every term in that vector, and this comes out to 13 over 35, 89 over 35, and 2/7. So that's my y hat, also known as the projection of the vector y onto the subspace W. And that's it. So it's almost not really any different from last class's stuff, except we're just upping the dimensions. Sort of a theme of the class, right?